Welcome back to Train Signal Cisco CCNP Route Training. Again, my name is Joe and I am your instructor. We've considered all of the parameters and ramifications of dealing with EIGRP, both planning and design, basic configuration, advanced configuration, and troubleshooting. We've done the same for OSPF. Now we want to actually be able to dig into BGP. BGP can be a little bit of a scary protocol because it's a little less familiar, it's different, and it has a lot of complexity to it. So we're actually going to begin by looking at the planning and design process for this protocol. In this lesson, we're going to look first at the unique characteristics of BGP. We're going to review when BGP would be your best design choice, planning methodology in approaching BGP, the verification plan, implementation steps, and transitioning to BGP from another protocol. First, we want to look a little bit at the unique characteristics of BGP, a little bit about the history and background. Because it is a path vector protocol, we want to look a little bit at the characteristics of path vector protocols. And we also want to look at some configuration issues unique to BGP. To begin with, you need to understand BGP from understanding the Internet, essentially. The first network that preceded the Internet was ARPANET. It was a single autonomous system that existed in the 1980s. They used what was called GGP, or the Gateway to Gateway Protocol, developed by BBN. There were several versions of it. There was versions 1 and 2. But they began to run into scaling issues. The successor to ARPANET was NSF, or the National Science Foundation Backbone. NSFNet, instead of using a single autonomous system, mandated that it be separate autonomous systems. BBN developed the Exterior Gateway Protocol, or EGP, which you won't find on newer Cisco routers, but you will on older ones. But EGP was deployed on the network to facilitate routing. And you can see it was in the 80s, 1982 range, but it quickly ran into scaling issues. It really had no ability to be able to detect routing loops, and it really had slow convergence, and it didn't scale very well. And you can see from the timeline on the left there were a number of just really important milestones in the creation of this protocol. So once EGP was considered no longer usable for routing on the developing Internet, BGP was developed by a number of different engineers. Kirk Lougheed, who was actually at Cisco, and Len Bosak. And the reason why I mention those names first is because they were in the original founding member group of Cisco. Len Bosak and Kirk Lougheed had actually worked at Stanford along with Sandy Lerner, to whom Len was married, and they actually developed the first Cisco router. It's a very long and interesting history by itself, which we won't go into now. But when BGP was being developed, Kirk Lougheed was actually listed on the RFC, and Jacob Rector from IBM, Jeff Honig from Cornell University, and obviously Len Bosak, these were people that all were mentioned in the document. The current iteration of BGP stands for Border Gateway Protocol, is BGP4. Version 1 was published in 1989, RFC 1105. Obviously, there was a need for revising it. Just 1 year later, BGP version 2 came out, RFC 1163, then version 3, and finally, the last version of BGP itself came out in 1995 with RFC 1163. Something that was added to BGP4 was what's called multi-protocol extensions. That was in the year 2000, and it was RF 2858 and 4760 in 2007, respectively. It's sometimes referred to as MBGP. BGP is a path vector routing protocol. It sounds similar to distance vector. It uses, however, something much more complex, so we want to look a little bit more about how the protocol operates. First, it requires, again, formal neighbor relationships. This shouldn't come as a great surprise. The neighbors, rather than using a separate IP protocol number, actually use TCP to establish connectivity. In fact, BGP uses TCP port 179. They are sometimes also called peers or BGP speakers. Now, they have to be explicitly configured. There is no multicast or unicast or broadcast discovery process that happens on interfaces. They have to be explicitly configured one at a time. So if there are 4 BGP peers, 4 separate neighbor statements have to be created and configured. There are also 2 types of neighbors. The first is internal, which is called internal BGP or iBGP, and these are BGP peers within the same autonomous system. There are also external peers, which is a great deal more common. It means that the neighbor is in another autonomous system. This is called eBGP. The database that's used in BGP is called the RIB, or Routing Information Base. It contains all the information about routes to destination networks, and RIB contents are actually local to a particular router. It just has to do with the way the protocol is constructed. And if you think about having to carry routes across the internet for some very large routing tables, it actually makes a lot of sense. The emphasis on path vector protocols is scalability. In other words, if you recall that EGP could not detect routing loops, that was one of the things BGP was designed to do. Selecting a loop-free route is the primary function and importance in BGP. As a result of that, the most efficient routes may not always be selected. Now, there are ways to manipulate routing, which we'll talk about later in our advanced configuration lesson. But BGP speakers don't have visibility into the internal topology of another autonomous system. In other words, there may be thousands of routers behind a particular BGP speaker running in that autonomous system's IGP, and really the BGP speaker, the eBGP speaker, doesn't have any visibility into that, doesn't care. All it wants to know is what's on the other side of that, what's being advertised. Obviously, because of the nature of dealing with lots of routes and neighbors and things of that nature, BGP is much more complex. There is a great deal more planning and design effort required, and configuration requires a lot more work. The routing logic that BGP uses is vastly different than what IGP use. Now let's look at some unique features of the BGP protocol, Border Gateway Protocol. To begin with, it is the protocol of choice for inter-autonomous system routing. Remember, intra means within and inter means between. So intra-AS routing is what IGPs do, and inter-AS routing is what BGP does. It's used extensively for global routing across the internet, for instance, specifically internet service providers. I began my career in IT at a small internet service provider in the Seattle, Washington area, and they used BGP extensively in order to be able to do peering with a particular peering point, the Seattle Internet Exchange, as well as their upstream providers. And essentially, the internal AS routing, the IGP, is essentially hidden from external BGP speakers. This is in order to be able to facilitate scale. Another thing that BGP does particularly well, again by its nature as an external gateway protocol, is support for aggregation or supernetting. For instance, my particular ISP that I worked for had a number of Class C address blocks, 31 I believe, if memory serves me correctly. And rather than advertising all those 31, they would actually summarize it into a single prefix. And that made route aggregation and supernetting much more possible. And it's also configurable on a per autonomous system basis. In other words, the autonomous system was my company's ISP connectivity. They would obviously configure what was going on in their autonomous system and advertise it out. And another thing that makes BGP unique from the other protocols is it uses TCP port 179 rather than using a distinct packet type or IP protocol type. BGP, rather than using metrics, uses what are called path attributes for selection. And this has to do, again, with selecting a loop-free route. There's no traditional metrics in the way that you would have been accustomed to with other protocols. There is something titled metric within BGP, but it's actually just another one of these path attributes. And there are multiple factors that can be configured to influence selection of routes. We'll go over those later. And the pattern by which it determines loop-free routes has to do with what are called AS paths. It actually tracks the various number of autonomous systems that a route passes through. For example, in the graphic to the left, you notice that router 3, its autonomous system 65004, and it's trying to get to network 10.1.1.1 in autonomous system 65001. So the path is going to be through autonomous system 65001, which originated the route. Then, because it's going from there to router 2, it's going through autonomous system 65002. So the path that shows up on 65004 is 65001, 65002. It would know then that there would be, for instance, if there's a direct connection between 65004 and 65001, all it would be was 65001, and it would select that route because it has a fewer number of autonomous systems that it's passed through to get there. It's just an easy way to understand how BGP operates, at least at the highest level. Now, there are multiple situations in which you use BGP. Obviously, as in the case of the ISP I work for, it's for internet connectivity, either single or multi-homed. Single-homed is just one connection. Multi-homed is multiple connections and or multiple internet service providers. BGP is also frequently used for connectivity to MPLS or multi-protocol label switching networks. I worked for AT&T for 5.5 years. We used BGP exclusively for MPLS connectivity. And then also connectivity to multiple autonomous systems. You may have some direct connectivity to another business entity. You want to be able to use some other protocol to sort of establish a network boundary, and you can use BGP to do that as well. You look at this as more of a private AS connectivity. Now we actually want to review when you would choose BGP over static routing, over OSPF or EIGRP or any other protocol that's out there. What would make you uniquely choose BGP as your protocol of choice? Well, first, obviously, and we've mentioned this already, for connectivity to the internet, for private routing between autonomous systems, for managing connections to MPLS networks, and then finally we'll consider some design principles for the border gateway protocol. Usually the first and foremost connection that BGP is used for is internet connectivity. It's not always required, however. When the internet was first getting established, it was obviously much more common, but most of the time, for instance, in our homes with Comcast or DSL or something like that, we're not using BGP. So it's not always required for internet connectivity. For instance, if a business entity has a single connection to one internet service provider, which is single-homed, there's no need for dealing with BGP at all, because there's only one point of input and one point of output for that particular business entity. It's also not necessary if you have multi-site connectivity to one or more internet service providers across a wide area network. You could still use static routing and weight the static routes to be able to know how to get in and out of that particular autonomous system, or even using an IGP. It's simple. You don't need BGP for that either. The other situation in which you wouldn't need BGP is if you already have publicly routable IP addresses that have been allocated to you by a single internet service provider. If you are operating using their internet-based globally routable IPs, you don't need BGP because they're doing all that work for you. Static default routing or redistribution into an IGP is often sufficient for the connectivity in these situations we're describing. And I can say that having assisted many customers both in my ISP days and in my AT&T days in setting up internet connectivity. However, BGP is advisable for internet connectivity under these following conditions. If you're operating a service provider environment, with not necessarily the size of an AT&T or a Verizon, but if you have a multiple internet connection service provider type environment, you need to use BGP. Another situation is you have what's called a portable group or portable block of IP addresses, which you have obtained from an internet routing registry. For instance, ARIN, or the American Registry of Internet Numbers, has allocated to your organization a block of static IPs that belong to you, that you have essentially leased. In that case, you need BGP because you essentially own those IP addresses and have to announce them up to the internet. It's also going to be necessary for you to have BGP if you're connecting to multiple ISPs, other than the way that we just described before where you're doing some kind of static routing. But you may just want to receive a static route from the internet service provider using BGP. You can get partial internet routes, and the way that works is they announce the routes within their network that are very specific. They announce those in some sort of summarized fashion to your business entity, and then there's a default route for everything else. It just makes things a lot simpler. You can also take in full internet routes. In order to demonstrate the complexities of the BGP protocol, we're actually going to use a device outside our lab environment called a route server. The purpose of a route server is to be able to give a point for network administrators to be able to test and determine reachability for IP networks on the global internet. Another type of environment which can accomplish the same thing as what's called a looking glass. It's usually a web-based type of portal. But we're actually going to be using AT&T's route server, which I've used on a number of occasions, both while I was there during my tenure and then following. So the host name is route.server.ip.att.net, just using a standard telnet session. Notice it's asking us to log in with the name rviews, route views. Now we can just look a little bit, show IP BGP. Notice there's an incredibly large amount of options. We'll do summary, because this shows configured neighbors and the number of routes per neighbor. Now notice here this is just a partial list. Identification of the neighbor by IP address, obviously version, which is 4. The autonomous system, AT&T's IP network is autonomous system number 7018. Messages sent and received. The length that it's been up, 10 weeks, 4 days, and then a number of prefixes that have been received. Notice here there are quite a number. These first two are much smaller, but then there are a number that are quite a bit larger. These are from different service providers, BGP peers, and so forth. Now, if we want to look at the actual BGP table, show IP BGP, we're going to dig more into what these mean a little bit later. But it actually shows a couple of things that are important. The prefix that's going to be reached, the next hop, and then it looks and shows the path. The reason why 7018 is listed first is because this is what this particular router, the route server, is going to be advertising to other BGP peers. It says that in order to reach this network, 10.0.4.0/22, its reachability is going through this list of autonomous systems. 7018, 4323, 7545, which is listed 4 times. We'll talk about what that means later. And finally to the originating autonomous system of 56203. Now if we wanted to look at routes that were originating from a particular autonomous system, we could do that. Let's pick this 56203. Do show IP BGP. You don't need to be concerned with these particular commands right now. Originating from that autonomous system. Because it's listed here, that's the originating point. And it's listing all the different routes. Now let's actually show the IP routing table. Show IP route BGP. Notice the vast number of prefixes that are listed here. A lot of them are /24s. Most ISPs will not accept anything smaller than a /24. I want to see one route in particular. Show IP route BGP 216.145.0.0, which incidentally is the block that my company that I worked for at the ISP. I could just do show IP route here at this case. Notice here, it shows 216.145.0.0/19, which is the single summarized route that's advertised by that autonomous system. It's an external route. It talks about all the different things that are involved. This is just a way of being able to show routes on the global internet and how they operate. And again, this route server can be very helpful when you're trying to troubleshoot load balancing issues or looking at how one particular network is going to be reachable. Another situation in which you'd want to choose BGP for the routing protocol of choice is when you're doing private routing between autonomous systems. Now, what does that mean? Well, it means that you and one autonomous system, one entity, one routing domain, interfacing with another routing domain, autonomous system, and so forth, but outside of your organization. Well, when would that happen? Well, you may be a part of a company that acquires another company. For instance, there was a large regional bank in the Pacific Northwest that I worked with in the past couple of years, that they were regularly acquiring smaller banks and bringing them into their system, and they would use a lot of different mechanisms in order to be able to make the new acquisitions a part of their network, and this is one way in which you could do something like that. It also helps you create definable boundaries between separate companies. You may be doing business with a particular business partner that you are exchanging information with, but you don't necessarily want to have a fully trusted relationship where they have access to everything inside your particular organization. So you would be able to use BGP as a way of being able to create a definite boundary between both. Also, if you're routing between another organization, even within your own company, that's using a completely different interior gateway protocol, BGP makes a very good translation point, peering point, exchange point in between the two types of routing protocols, rather than maybe just directly doing redistribution between the protocols. It's also helpful when you, as a network engineer, need to enforce some kind of policies regarding traffic that you're going to allow into or out of your network, because BGP offers a number of different capabilities in that regard. Another thing that BGP does very well, that I've had direct experience with, is for managing connections to MPLS networks. Service providers typically will use a number of different methods to connect. I want to introduce you to a couple of terms here, are the terms PE and CE. PE stands for Provider Edge or Provider Edge Router. It's essentially the boundary to the service provider's network. The network at the customer peers with the Provider Edge or PE router. The CE is the Customer Edge or Customer Edge Router. It's essentially the customer premise device that connects into the service provider network and is essentially the boundary to that particular site or organization for that particular entity. There are a number of different ways that MPLS actually propagates routes. Essentially, the way I've described it is it's like building a mini private internet, because that's basically what it is. One way is what's called static routes or pre-configured static routes. Essentially, the service provider builds a routing table within its own environment so that when something leaves a particular customer, and it's tagged with what's called a VPN header, so it's only going to go to the other sites that that customer has subscribed service to. Other customer traffic's not going to interact with it, but it will automatically know within the cloud where it needs to go next. Usually there's just a single default route that's sent out from each one of the configured remote sites, and then most of the magic is within the service provider cloud. The good news is that it's very easy to implement. The bad news is that you don't have any kind of visibility into the routing process if something's not operating correctly. You usually have to involve the service provider. Another method for connectivity is what we've been talking about up until now, BGP. It scales better. There's a process called AS override where you can actually use the same autonomous system at all the remote sites or different autonomous systems for each one of the remote sites. I've always been a fan of using the different autonomous systems per remote sites, again, because if there is something problematic, you can usually trace it down to a particular autonomous system that's been configured because the number's different. And then some service providers use an interior gateway protocol such as EIGRP or OSPF. And I've always, over the years, when MPLS first came out, heard a lot of complaints about why can't I just use EIGRP. And I actually heard an explanation, at least in the AT&T service environment, was with BGP, you are actually creating something that's designed to scale very large on the service provider side. But typically with interior gateway protocols, OSPF, EIGRP, you have to create separate instances of the protocol for each customer. And you could see where that would get very, very heavy on the router that's establishing the connections, whereas with BGP, it's just another autonomous system number. It's much easier to create scale. But I've seen this implemented many times with customers and service provider environments. So now let's just look at some general design principles for the border gateway protocol. First of all, if you're going to be using BGP for connectivity to the internet, determine what level of routing knowledge you need. For example, do you need a full internet routing table where you know about every prefix on the internet, kind of when we were just looking at the AT&T route server, so the thousands of routes that were being listed? Or do you just need partial routes, which means that all of the subnets and destination networks within that particular service provider's network, it will announce specific networks for, and for anything outside of its system, it'll just simply use a default route for you to get to those destinations? Or do you just need a single default route and that pretty much takes care of all your internet routing? That's one of the things you need to determine from a design standpoint. The second thing you need to determine from a design point is know what kind of connectivity requirements you're going to use. Are you going to be single homed, which means one ISP and one link, one point of entry, one point of exit? It's very simple and straightforward. A lot of small businesses use it, and it's typically when you get broadband internet to the home, it's the same kind of an environment. Then there is multi-homed, which means there is still a single internet service provider, but there are two or more links to that service provider. Now it could be multiple T1s, which can be both a bandwidth aggregation using PPP multi-link, or it could just be wanting to have diversity in terms of connectivity. So if one line fails, the other will take over. And this could be true whether it's T1s, DS3s, or some kind of Ethernet handoff. The single multi-home designation needs a little bit of explanation because it's here, it says one ISP, one link. A single multi-homed means you have one link to one service provider and one link to another service provider, and you're essentially using something like network address translation to sort of hide the complexity, or one may be primary, one may be secondary. But then you have dual multi-home, where you have two or more internet service providers with two or more links to your particular premise. So know what kind of connectivity requirements you need to have. Another thing you need to do with BGP is, when possible, summarize addressing to the lowest common denominator, the most general mass, to be able to cover correctly what you have within your network. You can use address summarization to announce summarized prefixes with the smallest and most efficient routes possible, which is what I just said. Being able to do that, for instance, with all the different networks in the old internet service provider I worked for, being able to go into one entry, 216.145.0.0/19, instead of representing a large number of /24 networks. Another thing with BGP is manually configuring your routing preferences. Remember that with BGP, it's not a traditional metric, but it deals with a number of path attributes, which we'll actually talk about in the lesson about BGP basics. You can use AS path manipulation, which is called prepending. You can do weight or local preference settings for what's going outbound, how to get out of the autonomous system, and then multi-exit discriminator, which essentially announces what point to enter the network through. And these are just a few of the many things you can do to manipulate route preferences. Another thing that can be very helpful is you can create BGP peering relationships either on the directly connected interface, well, not even necessarily directly connected interface, but on the interface that will reach that particular BGP peer, the physical interface or logical interface, or what's more recommended is being able to use peering over loopback interfaces. And again, the reason why is loopback interfaces never go down, and if you have multiple links that are available between your device and the neighbor device, it will be able to use any one of those. And if one of those links drops, it doesn't drop the neighbor relationship. So it can require for eBGP a multi-hop configuration, because BGP has a tendency to only want to use something that's directly connected or directly reachable. And if it has to do multiple hops, you use the eBGP multi-hop command or the neighbor command, which we'll talk about later. And again, it also allows for multiple physical interfaces to be used without interrupting the BGP session. You can also adjust the timers, but use caution, because changing the timers, you can shorten the convergence cycle, which is great. But if there is a problem with flapping interfaces, it can create all sorts of instability to the network. If you're going to use non-default timers, do it in a lab environment to determine your potential impacts, because there's nothing worse than putting in a big change to the network and it causing catastrophic issues. Now, as with OSPF and BGP, you want to be able to have a whole planning methodology regarding your use of this particular protocol. Some of this will be repetition, but the principles are very much still applicable. There are general network design principles to follow. You want to create a high-level design. You want to have a pilot or proof of concept testing, and then have a review and verification process of your design work. So whenever you're going to design a network, no matter what protocol you use, no matter what setting, no matter what service provider, you always want to start with requirements. Know your expectations. Don't assume them. Always make sure you know what they are. Be able to actually clearly articulate in a number of fairly well-phrased sentences what the expected outcomes are. Is it we want internet connectivity throughout the enterprise? Is it we want to be able to connect to this particular internet service provider? from a BGP standpoint, what is the outcome? Gather all of the facts. Make sure that you interview or talk to enough people, we call them stakeholders, to make sure that you understand what all the facts are involved, the number of sites and other things. Perform a physical site inspection so that there are no surprises. If a facility that you've never been to, it's even more important to do a physical inspection, as there are all sorts of surprises that can await you that you can avoid when you actually go to do the installation, test, and turn up. Account for power, cabling, and device placement. Make sure that you have network drops of the sufficient number. If it's a particular communications closet, that what's called the DMARC has been put there or extended to there. That's very important because some service providers will not do what's called an extended DMARC. Know the availability of your WAN circuits, how long it will be. 30 to 45 days used to be for a T1 and could be upwards of 90 to 120 for DS3 and above. Make sure you know what that availability is. And then also account for any devices that you're going to have to support in this new environment. Document all your assumptions, financial assumptions, who's responsible for what, whatever the expected timeline is for design, implementation, and testing, whatever other organizations are involved. Otherwise, you want to avoid to be able to have the finger pointing if something gets confused. Ask all questions, make sure that you confirm those, and get everything in writing. And if people get nervous about that, just stress the importance of having a paper trail. Develop your contingency plans and develop and stick to whatever a mutually agreed on project plan is a part of this. Make sure it's realistic as well. Make sure you have a high-level design, site locations, equipment, VLAN, LAN IP addressing, WAN links. If you're using autonomous systems at different sites, depending on what your end goal is. Develop a BOM or a bill of materials, equipment, lead times. Make sure you always have SmartNet maintenance, and then also whatever logistics of your staging are. Are you going to have them at your central office and then send them to remote sites, or is it going to be just shipped there and you will have someone work with it remotely and so forth? Make sure you have a very coherent IP addressing plan and that it's documented. Make sure you use consistent addressing, consistent masks, and just things of that nature. For instance, a /30 for serial links, a /24 for offices, and so forth. Reserve whatever ranges you may have for different purposes. For instance, I would usually recommend when a customer was putting in an MPLS network to use a really high address range like 10.254.254 because it'd be so unusual, it'd be very obvious in a routing table. Summarize what you can, track usage and decommissioning of addresses within the pool, and then take that high-level plan and turn it into detailed plans after you get the appropriate approvals. If necessary, do a pilot or proof of concept. If you're using a new technology, you're putting in new types of devices, if you're being acquired or are doing the acquiring of another company, that you have the ability to be able to deal with that. If you're changing the protocol, for instance, you're going from static to BGP, and if the processes are being different. The example I've used here is if you've used analog-based payment card systems at various locations and then you're going to move to network-based payment card systems. That's a huge impact. You want to be able to estimate anything you can in terms of how to properly and efficiently implement that. Understand that in a pilot or proof of concept, you need to know what your testing environment is going to be. It should be, from a scope standpoint, a subset of the number and types of sites that you'll have involved. For instance, if you have some sites that have 50 people and some sites that have 20 people and some sites that have 5 people, those are 3 different site types you can use. You don't have to replicate everything, just basically representative of the sites. Have the devices you're going to use. The staging of it should be essentially a lab miniature version of the larger network. That you know what your testing plan is, what the outcomes will be, and then how it will be reported, and how your lessons learned will be implemented in the larger project. It's important to have a verification and review process for anything that you do. So make certain that you have people that you trust to help you be able to smooth out the rough edges of your plan. You have peers, those that you know, maybe even in your department, experts, those, it may, for instance, if you have a Cisco partner that provides network and services and equipment, that would be a person or a group of people to be able to depend on. Cisco itself, those are the kinds of experts you want to be able to bring in. Ask your critics. Now make sure they're viable. If it's just someone that would tell you something mean just to hurt your feelings, they're not the kind of critics I'm talking about. I'm talking about the people who will be straight with you, that won't always spare your feelings, but you tell you what you need to hear. Obviously, you want to make sure your superiors, those to whom you report, have an input, and then also other reviewers as needed. So what are the implementation steps for taking care of BGP from a deployment perspective? Well, if you have a detailed project plan, which again comes from the high-level design, you have device-specific configurations, and then a series of verification steps. You need to have a document that helps you with your project plan. It should say who your stakeholders are, which is essentially anybody that has an interest in the project, be it superiors, end users, those that will be implementing, etc. The roles and responsibilities, whatever timelines or milestones, usually with specific dates and such. A communication plan for making sure any changes that are going to happen are properly communicated. Power cabling, device placement, implementation plan itself, outcomes, and what the criteria for completion are. If you don't know what it should look like when you're done, you're going to have a hard time of knowing when you're done. You want to have device-specific configurations for your layer 3 devices or your routers, host names, interface configurations, security configurations. I've always found it helpful to start with Notepad and write out in descending order, starting with the very general things that you need: host names, access, interface IP addresses, and then things that are more complex like routing protocols, and then things that are advanced such as security and remote access and those sorts of things. Make sure those are all taken care of within your routers and layer 3 devices. Layer 2 devices, also similar but may not be quite as extensive. Your host names, SVI, switched virtual interfaces, these are the layer 3 interfaces that are associated with a VLAN. You want to make sure you have those configured if you need them on that device. And then obviously VLAN, NTP, access, and whatever advanced configurations you might have for the layer 2 devices. There are a number of commands that you can use for verifying that your configuration is working correctly. First, just general connectivity. Show IP interface brief. It'll show you your IP addresses and what's connected and the state that it's in. Show CDP neighbors, helpful for Cisco devices. There's also another protocol called LLDP. That's something else that you may look into. Show environment all, shows what's going on in terms of temperature settings if your device supports it. Show diag shows all the information on how the hardware of that particular device exists. Show inventory. For BGP routing, specifically, show IP protocols. Show IP BGP summary, which shows the state of the neighbors as well as the number of prefixes that are being sent or received. Show IP BGP neighbor, which is a much longer output and shows you in excruciating detail what the BGP neighbor relationship looks like. Show IP BGP, the contents of the BGP routing table, and then show IP route BGP shows the routing entries in the IP routing table belonging to the BGP routing protocol. For debug commands, you can use debug IP packet or debug interface, just for general connectivity. For routing, debug IP BGP, the neighbor that's involved, debug IPE BGP events, keep alives, in, out, updates, and debug IP routing. Can actually give you visibility into the IP routing process and the BGP process itself. Finally, we want to take a look a little bit about the principles and building blocks of transitioning to BGP from another protocol. This can be, number one, if you are dealing with an internet connection and you're going to establish a BGP relationship to a service provider. It's also true if you're implementing an MPLS network in place of, for instance, internet-based VPNs or something of that nature. I have stepped customers through a number of times in transitioning to BGP from some kind of an IGP involved in this type of a network. And then obviously if you're connecting to another autonomous system and want to have that type of boundary. So we want to look a little bit about what it's going to be in a new or greenfield environment and then how to do it in an existing network. In a new network, here's the assumptions. Number one, a new network doesn't necessarily mean it's brand new from the ground up and it's the first time anything's been turned up. It could be that you're going from one service provider to another or one service type to another. For instance, back in the mists of time, there were a number of customers that were going from traditional frame relay hub and spoke networks to an IP-based MPLS network, and there was a lot of work that was involved in being able to transition that. Even though it was not necessarily a new network, there was a new connectivity that was being implemented. You might have, if that's the case, LAN addressing won't change. WAN addressing might. And there could be a number of protocols already in use. Static routing, EIGRP, OSPF, or even RIP might be in use to transition from those protocols to BGP. So in the transition process, if you have new equipment, by all means, use the new equipment with BGP, especially if there are new circuits involved. Just makes things a lot cleaner and easier all the way around. You can connect a little test network from the LAN side in order to be able to do some analysis to some maybe temporary IP addresses, just to be able to verify things are working. Have the full configuration available for the day of transition. Make sure it's all spelled out. Schedule your outage window if you have that kind of a process at your company. And then configure just the border routers first with BGP and transition whatever others you might need to on schedule. Now, if it's just a single router that's going to the new service provider environment, and you're just going to be switching LAN connections over, that could be fairly simple. Then you just disconnect your old devices with the new ones, then execute your test plan, make sure your BGP tables are properly populated, the IP routing table is up, that you can reach the other networks that you're anticipating, and then certify the network as being fully functional. For an existing network, it's a little bit more sticky. The assumption is, number one, the existing equipment will host the BGP networks. There's not going to be any new circuits. The IP addressing is not going to change. There's essentially going to be a hot cut from whatever the previous protocol is to the BGP protocol. In which case, you need to make sure you know a number of critical elements. How are you handling autonomous systems and site partitioning? If it's a single network connecting to the internet, you know what your autonomous system number is or should be, that's fine. But if you're using it for MPLS, are you going to use one autonomous system number using AS override, or are you going to use different autonomous system numbers from the private range for all your sites? That's what I would recommend, but you need to make sure you know what it is. Know what your transition plan is. Know what your testing plan is. And always, always have a rollback plan in case the transition to the new network, something goes awry and you have to be able to reinstate the old. So when you want to transition to BGP in an existing network, the transition process has to be handled carefully. First, you can configure your eBGP routers with a higher administrative distance. I'm suggesting 224 because eBGP has a default administrative distance of 20, which will trump any other IGP that you're using, including EIGRP. So you want to have something set artificially high so that it's not going to create disruptions. Now, if it's an iBGP peer, then it's an administrative distance of 200, which isn't going to trump anything. So that's a little safer. But you always want to be able to manually configure these things. One of the things by having this higher administrative distance is you can go ahead and establish your BGP peering relationships. They can be up, they can be functioning, they're not going to impact the routing of your network. You may be able to use just some dummy IP addresses from a completely unused range just as sort of a test point, but once the neighbor relationships are up, everything's functioning, you're verifying the type of reachability that you want, then you can schedule your outage window, and then you can set the administrative distance back on your eBGP routers to 20, and on your iBGP routers to 200, or you could just leave them there as it is. Once everything's up, you've made the transition, everything seems to be functioning, make sure you are seeing all the BGP routes correctly, that you're able to have full reachability to all the other endpoints, and once that's done, then you can certify your network as fully transitioned and ready for service. So just some key terms we want to review. The RIB, or Routing Information Base, this is essentially the BGP database containing all routes to destination networks local to a specific BGP router. iBGP, or Internal BGP, is a configured BGP peer or speaker located within the same autonomous system. eBGP, or External BGP, is a configured BGP peer or speaker located within another or different autonomous system. Understand the difference between iBGP and eBGP. Also recall that iBGP administrative distance 200, eBGP administrative distance 20. Single-homed is a description of a site or autonomous system which uses a single connection to the internet with one internet service provider. Multi-homed is description of a site or autonomous system which utilizes multiple internet connections and possibly multiple internet service providers. The PE router, provider edge, is the MPLS service provider devices and network boundary. And the CE router is the customer edge or MPLS customer premise-based devices. So a lot we covered in this lesson, a little bit about what makes BGP unique as a routing protocol, and there's a lot. When BGP is your best design choice, for instance, are you connecting to the internet? Are you connecting to an MPLS network? Are you connecting to another company that you want to have some kind of routing boundary with? A little bit about the planning methodology, design, planning, implementation, your verification plan for implementation, the steps for implementing BGP, and then finally transitioning to BGP from another protocol. Thank you for your attention. We'll be covering more on BGP in our next lesson.